Hey everyone, and welcome. Today we're diving into something that feels like magic, but is actually pure logic: how computers think. We're drawing on the fantastic research of Dr. Sudhindra S.G. to create this guide specifically for you educators out there. Our goal is to give you a super clear way to explain what's really going on inside the box. And it all starts with one big question.
I mean, really think about it. How does this thing, this hunk of silicon and metal on your desk, actually think? It feels like it should be this impossibly complex philosophical question, right? We use these machines constantly, but how do they get from a jolt of electricity to, running a complex program? Well, the secret isn't some kind of digital wizardry. It's actually incredibly simple. It's just logic.
So here's our game plan. We're going to break it all down. First, we'll look at binary, the language of computers. Then we'll jump back in time to meet George Boole and his algebra of logic. After that, we'll connect it to the real world with transistors and logic gates. Then the really cool part, how we build complex stuff from simple parts. And finally, we'll see how this powers, well, everything you do.
All right, let's dive into section 1. We have to start at the very, very beginning, with the only language a computer actually understands. It's called binary. And yeah, it really does all come down to ones and zeros.
So what is binary, really? Well, deep down, a computer is just a collection of switches. And a switch can only be in one of two states, right? It's either on or it's off. That's it. There's no in between. So we just give those two states a name. We call on 1 or true, and we call off 0 or false. This simple two-state system is the bedrock for literally everything a computer does, from showing text on a screen to playing your favorite song. You might be thinking, okay, but why just two states? Why not 3 or 5? And that's a great question. Believe it or not, some of the very first computing machines tried to use more states, systems called ternary with 3 states or even quinary with 5. But it just got, well, messy. It was way more complex and way less reliable. Binary, with its simple, clean, is it on or is it off question, just worked. It was clear, powerful, and, as it turns out, there was a whole system of math just sitting there waiting for it. And that brings us to section 2. We're going to hop in a time machine and go way back to the 1800s, long before anyone was even dreaming of a computer. We're going to meet a guy named George Boole. Now, Boole was a mathematician, but he was fascinated by an idea. What if you could use math to describe not just numbers, but logic? What if you could create an algebra for truth itself?
What Boole came up with was frankly genius. He said, let's forget numbers for a second. Let's say a variable can only be one of two things, true or false. Sound familiar? And then he defined just 3 basic ways to combine them. There's not, which is super simple. It just flips the value. True becomes false, false becomes true. Then there's and, which is only true if both things you're looking at are true. And finally, there's or, which is true if at least one of the things is true. That's it. Not, and or. These 3 little operations are the absolute foundation of everything computers do.
Okay, so we've got this abstract math from the 1800s. Awesome. But how do you actually build that? How do you make a physical machine that understands true and false? The answer, my friends, is one of the most important inventions of the 20th century, the tiny, humble transistor.
So what the heck is a transistor? Honestly, the best way to think about it is like a faucet for electricity. Seriously, it's just a microscopic switch. If you turn the handle one way, electricity flows. That's our on state, our true, R1. If you turn it the other way, the flow stops. That's our off state, our false, R0. Billions of these tiny little faucets are inside the device you're watching this on right now.
Now here's where the magic happens. We can take a few of these tiny transistor faucets and wire them together in some really clever ways. And when we do that, we can create a little circuit that physically performs one of Boole's operations. We call these circuits logic gates. Why? Because they literally act as a gate for electricity, opening or closing based on a logical rule. This is it. This is where Boole's abstract math becomes a real physical thing.
All right, section 4. We have our Lego bricks now, right? We have binary as the language, and we have these logic gates as our basic building blocks. So let's start building. Let's see how we go from these super simple pieces to the incredibly complex machines we use every day. First up is the easiest one of all, the NOT gate. I like to call it the bizarro gate or the opposite day gate. It has one input and one output, and its only job in life is to flip the signal. You send it a true, it spits out a false. You give it a false, it gives you back a true. Simple as that. It's an inverter. Next we have the AND gate.
And this one, well, it's the strict one. It's the bouncer at the club. It has two inputs, and it will only let a true signal pass through if, and only if, input A and input B are both true. If either one of them is false, or if they're both false, the AND gate says, nope, you're not getting in. The output is false.
Dr. Sudendra's research has this great kind of funny example. Let's say we have a statement. My name is Sudendra, and I'm wearing a blue dress. Well, if both of those things are true, then the whole statement is true. But what about my name is Sudendra, and I'm wearing a sari? Even if the first part is true, the second part isn't. So because of that strict AND, the entire statement becomes false. Both parts have to be true, no exceptions. Now, if the AND gate is the strict bouncer, the OR gate is its super chill cousin. It also has two inputs, but it's way more laid back. The OR gate will output a true signal if input A is true, or if input B is true, or if both are true. As long as there's at least one true signal coming in, the OR gate says, yeah, come on in, and outputs a true.
Okay, one more for you. This one's a little special. It's called the XOR gate, which stands for exclusive OR. Now, it's like the OR gate, but with a catch. The exclusive part is key. It means one or the other, but not both. The output is only true if the inputs are different. So a true and a false, that's true. But two truths? Nope, that's false. It's very particular.
The perfect real-world example is when you're ordering from a set menu at a restaurant. You know how it says choice of soup or salad? That's XOR logic right there. You can have the soup or you can have the salad, but you can't have both. It's one or the other, exclusively. That's exactly how the XOR gate thinks.
And this right here is the big reveal. This is how it all connects. It's called the ladder of abstraction, and it is honestly mind-blowing. So follow me on this. Step 1, we start with a single tiny transistor, just a switch. Step 2, we combine a handful of those transistors to make a single logic gate, like an AND gate or an OR gate. It makes one tiny decision. Step 3, we then combine thousands, millions of those gates to create a more complex circuit, one that can do something useful, like add two numbers together. Step 4, we then pack millions of those circuits onto a tiny sliver of silicon to create a processor, the brain of the computer. And step 5, that processor powers the entire computer. See what happened? Each layer builds on the one below it, while hiding its complexity. We went from a simple on-off switch all the way up to a computer, just by stacking simple ideas on top of each other. It's beautiful.
Okay, last section. So we've gone deep into the theory, but let's bring this all back to the real world. How do these simple little rules actually run? Well, everything.
The big takeaway here is that at its core, a computer is just a really, really fast logic machine. That's all it is. Every single thing you do, every time you click the mouse, tap your phone screen, type a letter, your computer breaks that action down into millions of tiny, simple, true, false questions. And then it uses those logic gates to answer them at incredible speeds.
Let's take a complex human decision, like deciding if you want pizza. You can actually model that with Boolean logic. Let's say a program needs to figure out if Sudendra wants pizza. The logic might look something like this. If your name is Sudendra, and it's after 5 p.m. or it's the weekend, and you're near a Pizza Hut, then the answer is true. It might seem silly, but honestly, every single app on your phone is just running much more complicated versions of this exact kind of logic all the time. So to wrap this all up for you and your students, what are the big ideas? First, computers speak a simple language called binary, just on and off. Second, we use tiny switches to build logic gates, like NOT, AND, and OR, which makes super simple decisions. Third, the real magic is that we stack these simple decision makers to create incredibly complex systems. And finally, remember that every single app, game, and website you use is built on this very same, very simple fundamental logic.
And so I want to leave you with this final thought. Think about it. Our entire digital world, all of its incredible complexity, was built from just three simple ideas: NOT, AND, and OR. That's a powerful thing to share with a classroom. It really makes you wonder, and this is the question for your students and for us too. What simple rules will be the building blocks for whatever comes next? Thanks for joining me on this explainer.